Welcome back, and here we are going to now apply some mathematics to some of the things we've been learning about fluids. So in the last video, we said a very important thing, and it's so important that it actually has a name, and it's called Pascal's principle. I guess we're writing in green today. Pascal's principle. And Pascal's principle is basically the idea that when you put pressure on a liquid, the pressure will push equally in every part of the liquid, in all directions. Okay? So we could write that down maybe. Pressure applied to an enclosed. It has to be closed in, because otherwise if you put pressure on a liquid that's in an open container, it'll just splash right out of the container. So you have to have everything closed in so that the liquid has nowhere to go, right? That's kind of the idea. You cannot pressurize a liquid unless it's closed up. It'll just slosh out wherever you have an opening. So an enclosed liquid is transmitted equally through the liquid. Transmitted. So what we mean is that each molecule begins to push on each molecule beside it. Right? So transmitted, and as each molecule pushes one on the other, it's kind of like a chain reaction, a domino effect. And the pressure gets pushed. One molecule pushes the next molecule, which pushes the next molecule, which pushes the next molecule, right? Here's some molecules. So what happens, of course, is one molecule pushes this one's pushing this one, and they're all pushing on each other. You can imagine the crowd of everybody pushing on each other, and eventually the ones near the edge are pushing on the edge of the container, like this. And of course, the container is closed in, and it's strong enough, hopefully, so that they can't get out, so that they can't go anywhere, and that force, or that's being pushed all through there, creates what's called pressure, right? So it's transmitted from one part of the liquid to another. That's what we mean by that. Transmitted equally to every part of the liquid. Okay, and that's what we were talking about last video. Now we're giving it a name. Pascal's principle. And of course, and to the container. That pressure is also being forced against the actual thing that's closing it in, the container, right? So that's why when you put things under pressure, you have to have strong containers that aren't going to burst open. Okay. Now, we used Pascal's principle then to apply this sort of numerically to a system of pistons. And so I'm just going to show you now how we'll mathematically use that. So let's take a piston system like this, okay? And we'll take our small piston and down here, and we'll have a much larger piston on this side. Okay, good. And we'll call this piston 1, and we'll call this piston 2, let's say. So what we can, well, we could do, instead of 1 and 2, maybe it might be easier if we use large and small, right? Because obviously this is the small piston, so we'll use an S for the small piston and an L for the large piston, and that way it'll be easier maybe for you to keep track. So the small piston, we're going to apply a force by pushing it down, and that force will create pressure, and that pressure is spread out over the area. So a downward force here creates pressure, pushing up and in all directions, all through the liquid, right, everywhere, all the way over until it pushes up over here on this side. But we have to look at the area. Pressure is force per unit area. So the pressure we're creating at the small piston can be described like this. This is the pressure at the small piston. And it's going to equal the pressure at the large piston. That's what Pascal's principle actually says. So I can rewrite this as force and area. So there. So that becomes that. Now, let's say we have some information about a particular press. Let's say that what we have here is a platform, and on this platform is a car, and we want to lift that car. So let me give you some information. The mass of the car is going to be 1.4 times 10 to the 3. So that's about 1,400, right? 1,400 kilograms. So there's the mass of our car. And then I'm going to tell you the areas of some of the pistons involved. So the area of the large piston, AL, is going to be about 0.22 square meters. Now that doesn't sound very large, but it actually is quite big if you think about it. Because you have to think a square meter is basically a meter by a meter. It's a box, a meter by a meter, right? So just so you get an idea, if you took a box, a meter by a meter, well, a 0.22 of that, it's about a quarter, right? It's about 1/4 of that. 0.25 is a quarter. So that's how big it would be. It would be half a meter by half a meter. That's a pretty big area. 50 centimeters by 50 centimeters. So don't be fooled by the fact that these numbers look small. They actually, when you're talking about square meters, they're actually fairly sizable. Okay, so let's say I told you that much, and I asked you a question, and I said, how much force, let's get our pen back here. How much force is needed at the small piston in order for the large piston to raise the car? Now, I'll make another little point here. Whenever we raise things, we want to try to keep things as close to constant speeds as possible and relatively slow speeds, because remember, if you want to accelerate, you need extra force. We're talking here about a balanced pressure on both sides. And so there is obviously a slight acceleration when we go from 0 to moving. But if we minimize that minimizes any extra forces that would be required to accelerate the piston. We don't need this car to go up faster and faster and faster. We want it to just go up nice at a regular constant speed. So we have to kind of remember that all of these things work when we assume that we're moving at constant and relatively slow speeds, so that any accelerations are very minimal and are so small that they don't affect much. Okay? So in order to raise the car, we want to raise up the car. Okay, let's draw ourselves a little picture. So again, what I have is a small piston. I think it was on the left. Let's redraw our picture, maybe, just so we can see. But I'm going to draw this more like a free body diagram with the forces involved. So at the small piston, this is the force of the small piston. That's kind of what we're trying to figure out in this question. We don't know what that is, right? But what about the force at the, do we know anything about the force required at the large piston? Well, the large piston is attached to a sort of a platform with a car on top. Okay? Now remember, a car has a mass, which means there's a downward force of gravity, Fg, which is the weight of the car. When you lift something, remember, you have to apply a force equal to its weight. So if we want to lift this piston, this force of the large piston lifting up, it has to be equal to the weight of the car so that we can lift it. And of course, the weight of the car is the force of gravity, which is mg. So we can determine how much force the piston has to push up by simply considering the free body diagram. If gravity is trying to push down on the car, then the piston must push up with an equal force to lift it at a constant speed. Because remember, constant speed means forces are balanced. The net force is 0. The net force here is equal to the lifting force of the piston plus the gravity. But if we want this to be a 0, right, then that means these two forces must be exactly the same. Because one is down, so it's negative, right? This is a negative force and a positive force. So that's how we remember all that. So now I know what the force is that I need at the large piston, because I know what the mass of the car was. Remember, it was 1,400 kilograms. So I know that this has to be 1,400 multiplied by 9.8. So that's an easy thing to figure out. The weight. When you're lifting things, always think about weight and always think about the force of gravity. So that means there's a force of 13,720 newtons, fairly large force necessary. Okay. Now, I think I neglected to tell you one more thing. So I'm going to go back here and just pretend that I told you this before. We also need to know the area of the small piston, which I didn't get to. So let's say that's going to be about 0.013, very small. See how much smaller that is. So that would be given to you too in this case. You basically have to be given any three of these four things, right? There are four things that we can do with numbers. So you have to be given three of them, and you can always find out whatever the other one is. Okay, so let's put it all together now. We go back to that statement. The force of the small and the area of the small equals force at the large, area at the large. Well, we don't know the force of the small, but we do know the area. I told you that just now. So we'll go back up there, 0.013. Over here, we now know the force at the large piston. It has to equal the weight of the thing we're trying to lift. Okay, so that's what you have to remember. And then the area of the large piston was 0.22 square meters. So we can put that, 0.22. And now we can see how this can solve. We're going to cross multiply this. So we're going to put the Fs and we're going to multiply the 0.22 over there. And then we're going to multiply the other two like this. So we get a nice simple equation. So 13,720 multiplied by 0.013 is going to come up to about 178.4-ish. Okay. We're not using significant digits here, so we'll just kind of not worry too much about the rounding. Now to solve this, we divide both sides by 0.22, right? And we see that we're going to get a large enough force, but smaller than what we had before, divided by 0.22. So that comes out to about 811 newtons, give or take. So in order to lift a car that would normally require this much force, that's the weight of the car, we're able to lift it with only 811 newtons of force. That's much less. And that's because of the difference in the areas and the fact that the pressure has to be the same. Pascal's principle. Okay, let's ask ourselves some other questions. What is the pressure in this system? How much pressure is actually in the liquid? Well, to find the pressure, all we have to do is remember that pressure is force per unit area. Now we have two different forces in two different areas, and it doesn't matter which one we use because Pascal's principle says the pressure is the same everywhere in this liquid. So we can use the big piston to find the pressure, or we can use the small piston to find the pressure. It's our choice. It's the same everywhere. So it equals the small piston, and it also equals the large piston. So we don't need all of this. I'm just showing you. So we could either do the small one. We could do this one, which is 811. That was the force over the area, which I think was 0.013, right? And that would work out if we did the math. Let me just do a quick calculation here, and we divide that about 6,2,385 pascals of pressure, or 62-ish, 62.4 if we round it off, kilopascals. Now, I'm writing this sloppy, so it's a small k, it's a capital P, and a small a, kilopascal. So over here, you see my P. P's are weird. They sometimes look large or small depending on how you write them. So it's actually a capital P and a small a. We should write that the proper way. Okay, or we could have done the large piston. It doesn't matter, so you can do one or the other, right? If we do the large piston, well, that force was much larger. If I go up there, 13,720, but it also had a much larger area. Its area was I believe 0.22. We'll go all the way up and check. Yep, 0.22, 0.22. But when you do this division, you should get a number almost exactly the same as what you got before. All right. So I'm getting about slightly different. It's 62. This one came out to 2.7. And that's because, of course, we rounded off a lot of our numbers, right? And so this number here and this number here, they're essentially the same number. It's just they differ because of rounding. There is a thing called significant digits we could use to get it to come out perfectly, but we haven't studied that yet. So we won't worry about that. But basically, you can see that this is about 62. This would be 62.3 kilopascals, right? Those numbers are virtually the same. They're both rounded off to 62 kilopascals. So we know that we're on the right track. Both answers are correct. And that's how you can figure out a couple of different things. Now, we can also figure out how far the pistons have to move, right? Because remember, you've got to think about the distance. So let's do one more little calculation. Let's go back and add some information. Let's say that when we did this, we wanted to lift the car, right, high enough so you could get under it. So here's my car again. There it is. We wanted to lift the car, let's say 3 meters in order to be able to get underneath the car and work. So now how far would we have to push the small piston down? Right? I didn't draw the piston there. How far would we have to push that piston down? Well, again, we could understand that the work done in both situations must be equal. So the work done by the small piston must also equal the work done by the large piston. And the work is the force times the distance. Force times distance. And we know what the forces were. The force at the small piston was about 811, give or take. And so how far will that small piston have to go? Maybe I'll put S's here and L's here to remind us. Well, we know the force at the big piston, that was the weight of the car, right? And it was quite large. 13, go grab it, weight of the car, 13,720. So 13,720 multiplied by the D time, we know how far we want this car to lift. We want it to lift 3 meters, so we need to multiply that by 3 meters. And you can see again how you can figure out the math here. So if we take the 13,720 and we multiply it by 3, it's going to be 41,160. And then we have to divide both sides by 811. Divided by 811, so we'll divide that number by 811, and we get about 50. The distance that this would have to move is actually 51 meters. 51 meters, that's incredibly long way. So what this means is the example of this lift is probably not very practical, right? In other words, how could we fix it? How could we make it so that we don't have to move this half a kilometer? Or sorry, no, that wouldn't be half a kilometer. 51 meters. It's still a long way. It's like all the way across a room or more, a very large room. So if we were going to move that this far, that means that the design is bad. So the way to fix that would be to go back to the very start, right? The way to make a better system would be, see these areas that I told you? Well, those aren't very good. If you were a designer, you'd say, nope, I got to fix this. So what I have to do is I have to make the difference between these areas bigger. I either have to make this area even larger or this area smaller. I need a smaller piston or a larger piston. I need to change the given information so that I can generate even bigger forces. And of course, then this might be reduced down to 3 meters or 5 meters or 6 meters. Well, it would never be 3 meters, would it? It would be, you know, maybe 10 meters or something like that. You would have to increase or decrease the areas to make this work. But that is the answer, even though it doesn't seem very reasonable to push something 51 meters. That is the answer according to the given information here. And that's how the process by which you could figure things out. So there's 3 examples. Remember, as I said, we did finding the force of the small piston, but you could find the force of any of these or the value of any of these areas or forces as long as you knew 3 out of the 4, right? And remember, this one is very often the weight. You might not be given it, but if you're given the mass of the object you want to lift, then mg is the way you figure out the force of the large piston. And that's all there is to say about that.